Good morning, mathematicians. We're back at it. We still have Brauer groups in the title, but we have now finally broached the subject. Whoa, why did yesterday's... Hang on, let's go look at these numbers for a second. Usually my live streams are around like 150 or whatever, but yesterday only got 90 views. What's up with that? Hang on, let's go look at these numbers for a second. Yeah. Anyways. Let's pop out chat. And let's get to it. Maybe they were tired of me putting Brauer groups in the title. And the algorithm got mad. It is like Groundhog Day, except if things slightly modified. Because in fact, it is... today says Groundhog... sorry, I almost said Groundhog groups. Brauer groups and cohomology. So it's slightly different today. Okay. Let A be a central simple algebra over K, and let K be a field containing K. It sounds so funny to say out loud. Not necessarily a finite degree. Then, if we tensor up, this should still be simple. Earth Pig Day. Yes, I agree. It is Earth Pig Day. The same argument shows that the center, as this proposition, shows that the center should be K. Sure. Also, the proof of lemma 2.7 does not use that D is finite dimensional over K. Therefore, when A is a division algebra, every two-sided ideal is generated as an A module. Oh, right, by its intersection with K. Right, I remember us doing that. And therefore is 0 or the whole thing. And then we do a little magical tensor rearranging presto, and that thing is simple by tensor product stuff. Great. Hello, Arad. Hello, Arad. For a central simple algebra, A over K, the degree... I'm still confused about what this means. I don't know what the degree means. I still don't know what the degree means. The dimension of the K basis? Clearly the degree of A over K is the degree of... what? Does dimension it? Okay. If we're going to trust AI, which we shouldn't. No, maybe we should in this case. It's probably right in this case. But then why is that equal to this? Why is that clear? I guess it makes sense. No, okay. I believe it. Right. You just if you have a basis of a k basis of A, you just take those basis elements and tensor them by 1, and that should be a k alg basis. Okay. And we know that this is equal to this. Okay. Matrix algebras have square dimension over the ground field, so it makes sense. That's what the notation means. Yeah. Let L be a different field, or whatever, some field containing K. Then, right? And that, and, oh, boyja. And this tensor product can get rearranged as such. It can get rearranged again. Wait, n squared minus 1? What's n squared minus 1? Yeah, that's GLN. Oh, I see. The point is that we get a homomorphism. Tensoring up gives us a homomorphism of Brauer groups. And then the relative Brauer group, I guess, is that what we would call it maybe? Is the kernel. Consists of the similarity classes represented by central simple K algebras such that this is a matrix algebra. Okay. A central simple algebra, or its class in the Brauer group, is said to be split by L. And L is the splitting field if we can tensor if tensoring up gives us a matrix algebra, right? Thus, this consists of the elements that are split by L. Cool. I like these sort of rationality kinds of questions. For every field K, the Brauer group of K is the union over all the finite extensions in some fixed algebraic closure. We have to show that every central simple algebra over K splits by a finite extension. We know that this is true, and that there exists a basis such this is true. Because this is the union over all of these, the EI, J must all lie in this for some K. Nice. I guess I'm still not over this, whatever it was. I thought I had defeated it. That was my mistake. I got cocky. But, I mean, I feel fine. I only felt like garbage the first couple days. Okay, for a Galois extension of fields, so here's the big thing, that the Brauer group is actually recovered. The Brauer group of L over K is recovered by the second Galois cohomology. But first, we need to investigate the maximal subfields of a central simple algebra. You've wondered if the terminology of split in CSAs is related to the splitting of primes in a precise sense. Certainly of this same vibe. That's a good question. That's a good question. I mean, my assumption was that it was just more similar to the way, well, mind you, I guess polynomial splitting is related to that. But my original thought was more, I was thinking about like representations and representation theory, and when a representation splits. Yeah, like if you have a representation and then like you go to an extension and then it's like you have like an irreducible representation, but then you pass up to a larger field and then it becomes reducible. I mean, I guess it is still spiritually similar. But is it true in a precise sense? I don't know. Okay, we need a variant of the double centralizer theorem in which MNK is replaced by a central simple algebra. Was the double centralizer theorem just about matrices? I thought we had a result in more generality. Maybe I'm misremembering. Okay, let B be a simple K subalgebra of a central simple K algebra A. Then the centralizer of B in A is simple. And B is the centralizer of C. Isn't that kind of weird? Wouldn't you think that a simple algebra wouldn't have simple subalgebras? But I guess that's not true. Yeah, I mean, it makes sense. I mean, I guess if you think about a ring, yeah, what am I saying? It's not that crazy. And moreover, we can stack dimensions as such. Okay. Suppose that V, let V denote B. Oh my God. I feel like this is, I don't know. Why don't we use like B sub K or something? For me, that's better notation, but oh well. Regarded as a K vector space, then B and B up both act on V, and each is the centralizer of the other. As K endomorphisms of V. Consider the central simple algebra where we tensor up by K. Proposition 2.3 shows that the centralizer, B tensor 1, in this algebra, the centralizer of what? Of that algebra? Wait. 2.3. Right. Okay. Right. The centralizer of B1. Oh, in... right. Okay. Yeah, the centralizer of B tensor 1 in this thing is this thing. Yes, I agree. And that of 1B is going to be A tensor B op. I agree. On applying nether scolum to the two embeddings... oh, nice application. Okay. We get an invertible element that conjugates them. Huh. And so therefore it must conjugate the centralizers, which shows that they're isomorphic. Very cool. Very cool. Very cool. And then it allows us to say that this is simple because this is simple. And, wait, this implies that C itself is simple? If I could use my own notation to write things down, well, yeah, maybe I should. I probably should be doing that. Yeah, I do wonder, does anyone know, like, I guess maybe, even if I download the PDF, there's, like, other things that go up top. Like, how can I make a view where it takes up essentially the whole window and I don't have any of these extra damn boxes around? And then I would want to do the same thing for OneNote. And that would just make everything fit a bit better on my screen. Ah, c'est la vie, c'est la vie. Okay, why is C simple? For every ideal, A of C, tensoring up the ideal is an ideal of this thing. We already said that was simple, so shouldn't that already force that ideal to be everything? Shouldn't that end the argument here? Why does the argument keep going? Oh, Lord. As this has degree this squared over k, the degree of this thing over k factors as such. Oh, okay, maybe that does... Oh, yes, that does end the argument of the simplicity of C. Okay, good. Although... I mean, it makes sense to me that it follows, but, like, one could imagine... I don't think it's crazy to imagine a situation where this ideal is somehow lacking some things in C, but you still, after tensoring up, end up getting everything. Does that make sense? Because B is a subalgebra of A. So, like, that doesn't seem totally cuckoo wacko to me. Then again, we've got nice tensor products. Everything's, like, over a field. Everything's a vector space, so... Yeah, I guess by, like, a dimension count. By a dimension count, it has to hold. Okay, so this has this degree, so we know that this splits as such. And obviously, this is true. I agree. Comparing these equalities, we find that... right, because these two things are equal. Do some cancellation. Yes. Okay. And isn't that what we wanted to show? Why is there one more sentence? If B prime denotes the centralizer of C, oh yes, now I see why there's one more sentence. If B prime is the centralizer of C and A, then B prime contains B, but then after the above, we can plug this in, and these have to be equal. Nice. Very nice. Okay. gang, are you with me? Maybe we gotta do something, maybe we gotta take a break from this. We gotta do something more exciting. Only 90 views on yesterday's video. We didn't even break 100. Chat is not popping off with random questions today. Ooh, but this looks cool. I wanna compute some Brauer groups via cocycles. That seems like a cool thing. I don't know. Maybe it is about time to like take a break tomorrow and talk about random other stuff. Oh, but Brauer groups of special fields. We're gonna prove some stuff. Man, that looks kind of cool. Half with you, half with your own math. Yeah, that's actually the ideal. That's the way to be. If I was watching someone's live stream, that's exactly what I would be doing. How good is my functional analysis? I would not say it is very good. I know some stuff. I've TA'd analysis 2 a couple times now, which is like basically intro to functional analysis. Of course, my research does kind of involve some functional analysis. And like right now I'm in a reading group, or I'm part of a seminar on the orbit method, which I probably should be studying for more, but that definitely involves some like harmonic analysis and functional analysis. But I wouldn't say it's very deep. I wouldn't say I have a depth of knowledge in the field. But there is a part of me that would like to lean more into that at some point. Do I know about projective tensors? Or how do you topologize tensor products of topological vector spaces, such as Banach algebras? Oh, that's interesting. I'm trying to think. Actually, I thought I had this. I thought I had this document saved somewhere. Oh, where am I going? I'm a mess. Yeah, I thought I had this PDF saved. Maybe I can find it. Hilbert spaces do not have a tensor product. I mean, they do, but yeah, I think it was this PDF from Paul Garrett, Absolute Chad. I think the point is that the tensor product of Hilbert spaces, I mean, of course, we can define such a thing, but it, so this is not quite what you asked. This is like, you were asking about like Banach algebras, but it just made me think of this, which is interesting. Yes, you're right, Mastrek. We can define a thing that we call the tensor product, which is the topological completion of the algebraic tensor product. However, the point of this document is that from the categorical perspective, if you write down, like, according to the universal property, what should be the tensor product, then you find that this thing that we call the tensor product does not actually satisfy the universal property that you would think. And this is really, a matter of topology, I suppose. I mean, you can go read Paul Garrett's note on this here. All right, so like he said, it is possible to put an inner product on the tensor product, on the algebraic one, and then take the completion, and you get a Hilbert space. However, as he says, this Hilbert space fails to have the universal property, which is what he argues here. So, which is fine. Our lives go on just fine, without this being true. But it's interesting. I also don't know what projective tensors are, to be honest. New wave infantry. Does condensed math resolve this? That sounds cool. The projective tensor product of locally convex topological vector spaces is a topological vector space structure on the tensor product. It is the strongest topology, which makes this locally convex, such that the canonical map is continuous. And this is called the projective tensor product. Okay. Why is it called projective? Because I guess somehow it's generated by projections down to the individual factors or something. Oh, and this thing does satisfy a universal property. That's interesting. Huh. In the pigeonhole principle, can I help you when applying this principle on a question? So how to determine what to consider the objects and what to consider the boxes. I'm not sure what to say in general. It really depends on the setup of the question. It really depends on the setup of the question, yeah. So without specific examples, all I can tell you is read a ton of examples, and eventually your brain will get good at recognizing the pattern. Yeah. Okay, should we go back to this for a minute? And then probably pop off soon-ish. In the case that V is a vector space, theorem 3.1 follows from 114. I don't remember what those are. Because V will be a faithful semi-simple B module. Okay. This observation can be used to give an alternative proof of the theorem because A becomes of this form after a finite extension to the base field. Do I know about representations of SLN-Z over a field with characteristic 0? What the hell is all that banging? Man, living in an apartment is weird. Do I know? I'm curious as to why you specifically, Nerdy Quagsire, are asking me about this. I guess in short, the answer is no. I guess I've never really thought about the representations of SLN-Z. Like, what kind of group is that even? I guess it's an algebraic group over the integers. I guess. And my assumption would be I do know about the representations of SLN-C, and I suppose that probably one could leverage a lot of that theory. You have to do reading on that? Okay. I might have to think about it's possible that Humphreys could touch on some of this. Okay, I'm really confused about this banging I'm hearing. I might go because this weird banging. What What the hell is happening? Okay, well, I'll just say, Nelson, off-topic question. I am interested in homotopy type theory and univalent things. I haven't really thought carefully about it for a while. But actually, if you go to my channel, I have a video called Hot Boy Summer. Actually, I should just go to my channel. I have a video where I talk about the summer school I went to in Italy, where I learned about homotopy type theory and proof assistance, in particular the proof assistant rock, as it's now called. What a bummer! Only 1.6 thousand views. Look at this beautiful plentiful background here. Actually, the first part is a little bit cringe, and it's just me talking about my trip. But I do go on and read more about, talk more about some cool homotopy type theory type stuff. Okay, the banging ended, so maybe I'll read a little bit more. If in the statement of the theorem above, B has center K, then so also does C, and the canonical homomorphism from here is an isomorphism. Wait, what? B and C? That is a very cool kind of duality statement. If the centers of B and C both equal the intersection, so B central implies A central, and therefore this is central simple, which implies that has to be injective, and it's surjective because the algebras have the same dimension over K. Right. Neato. Okay, is this where we leave it off for today? Maybe. Yeah, I think this is where we leave it for today. Okay, where do we pick things up tomorrow? Kind of looks like some boring theorems coming up next. Who knows what will happen tomorrow? Okay, well, thanks for joining me. And as usual, QED.